Okay, so I have a little bit longer. So we're back to designing OFDM. So how do we do Wi-Fi design? And so far, okay, I think what we heard is basically that what Wi-Fi is doing is taking your signal in time and converts it in frequency. So as if your symbols in frequency would be so. If you see this signal you're sending in a spectrum analyzer, you will see in different frequencies the symbols you're sending. So for example, if you decide to put zeros here, right, in spectrum analyzer, you will not see any peak in this area. That's why when in this particular example in a code, when I was actually running this example where I send only one, everything is zero except for this one, I just saw this sign, right? So that's the idea of IFFT. I mean, I guess most of you are probably aware. But the reason why we do IFFT there is we want to make it, to shape it in frequency, right? Now, that's what we do, but okay? I touched something here. Okay, now better? Yeah, sorry. So that's what you do, and now I'll try to explain why we do that, right? So basically, this is just a high level thing you have to do with any OFDM symbol, be it with any OFDM communication, be it Wi-Fi or LTE, or they all have these things. They have pilots and they have Cyclic Prefix, right? So now I'll try to explain why they have these, right? Okay, so I guess most of you know what the channel impulse response is. I'll just run a simple example saying basically I'm just going to create one simple impulse, okay? So here is the simple code. Basically what I do, I send 31 zeros, 2 times 1, 31 zeros, okay? And then I just plot that. As simple as that. Almost not, let's see if it runs. So, oh, I have a new one here. Sorry, now I can't close. This is my symbol, okay. Yesterday it used to plot all on the same one. Okay, so so this is kind of obvious, but basically so I just created a symbol, right? So I just do like 31 zeros, 2 ones, and 31 zeros, right? So that was the basic thing, nothing special here. Now what I'm going to add into it, I'm going to do the same code as here, right? I'm just going to add a channel. So a channel is something I kind of artificially created, which is kind of similar to what you would see in nature. Not fully, but so let me show you what the channel is. So the channel is basically doing the following. So it's taking, so I'm creating some arbitrary channel here, but basically what channel has its stop. So what happens in nature is you send this signal, right? And basically if I'm going to go all the way in there in the corner, there will be a direct line of sight there, and there'll be reflections of different places, right? So you'll see a copy of a signal, attenuated and shifted in frequency and shifted in phase, coming there, right? Because of it transfers different paths. So again, there's lots of nice theory behind it, but so what happens here is I'm just taking my signal and I'm taking delayed copies of my signal and I'm multiplying in time. So basically one copy will reach you directly. The other copy will be delayed by one symbol. I will come a bit later with some kind of random phase or amplitude change. There'll be another copy coming later, another copy coming later. So this is just a mock-up code for this signal. So basically what I do, I have this kind of sliding window, okay? So what I do, at 0, I always keep the last received bit, okay? And then the other bits I just shift around. I just copy 11 out of 12 bits, always kind of shift out, like a sliding shift register. And then I multiply these with taps. So basically saying, the previous copy that I sent before is coming and hurt me now with multiply with different tap. So that's basically a very simple model of multi-path channel. And so this is another kind of bit that illustrates the coding. So we have this vector library, which is just a fast way of doing multiplication, right? So I have vector y, which is the output. So y equals this times that. And this is just a shift, so we normalize for precision. So you can ignore that. So basically I have all this delayed copy of my signal, including the fresh copy, which I multiply with my top vector, which again defines me what is the effect of each part. And typically it's going to be decaying, and in this case I kind of get some weird, so it doesn't matter. And basically I multiply these two vectors, and I sum them all up. That's my multipart channel, and that's really what multipart channel is. So the only difference is that what are these numbers in the channel? Here I just create some random things in the channel. Okay. So when I now go here, and so now what I'm doing. So this was the thing we just ran before, right? This is the thing when I just send a symbol here, right? So let's see what this thing is what's gonna happen when I run this through a multipart channel, right? So now this code is exactly the same, except that I have here test channel, right? So this is running my channel on the top of it. So let's see. Why is it creating new ones every time? No, this one. No, this is still the old one. Thank you. Let me just try to restart it. Okay, sorry for this. I'm hoping this is going to work better now. I can assure you yesterday at night in my room it worked perfectly. So it's always the... Right, so here's my second try, my new line. I just did the I'm compiling the wrong one. Suppose this is the one. Yeah, this should be the one. Right, so basically what happens is, so this is a funny multipart channel, but you see that what I send as a symbol, it kind of gets some echo, it gets repeated a little bit. And so typically it should be decaying. In my case, I guess I just picked a funny one, but it should be kind of going down. And so what happens, it depends really what is the distance of your communication, how many, if you go very nearby, for example, if I just talk to Ram, the thing that reflects off the wall and coming back is probably going to be much more attenuated compared to what I actually send to him. But if I go very far away, some of these parts are going to be comparable, right? There's this two-way reflection model, meaning that if I talk to someone all the way, maybe 100 meters back, the part that reflects over the floor and the part that goes directly line of sight are going to be of the similar power. So it's very difficult to predict this thing happens, and you'll have some kind of channel impulse response, which is unknown, unpredictable, and we have to deal with it. So that's the kind of the effect it has on it. So basically now what it does to my symbol. So next thing I'm just going to...
Did you actually use and collect the samples on the receiver and see what happens, or just a two sample white balls? I was curious because at least I've done this using sound, right? Two samples, at least in microphones don't even pick up. It takes some time for the... So I guess in here...
Yes. It wouldn't react. So we did it previously, but we did it with FFT, right? So we did the inverse and we collected this from the FFT. It didn't do it, yeah.
But in a real thing, if you actually ran this code and if you had used if you had collected samples off of the
it wouldn't work because, as precisely as you said, it won't have enough time to wrap up all the amplifiers and analog parts. Yes.
So you might have to have a wider
Yes.
impulse, and
Yes.
then you might have to see what happens.
Yeah. So this was just to illustrate. Yeah, but I agree. So basically, I guess the better way to do that is you can just send an arbitrary known sign, well, OFDM symbol, and then equalize in frequency. That would be a better way.
Or typically you scan sign with different frequencies.
Right,
and
yeah.
all that, right?
Yeah. Depends on your bandwidth, I guess. Yeah. So, right. So the effect on the waveform. So basically, what am I doing here now? So now I'm back. So this was a funny example where I'm sending my. Let me run it while I explain it, because it does take some time now. So basically, what I'm sending here is I'm just sending. I'm doing the QPSK symbol. So basically, I'm doing my mock transmitter. So I take some bits. I forget about scrambling interleaving because that's not essential to. It's essential for the receiver, but not for the demonstrating the waveforms. I'm just creating some QPSK symbol out of it, and I'm sending this to IFFT, and I'm plotting the output, right? So this is the same IFFT we've seen before, and then hopefully the output should now be there, right? So this is my FFT, and this FFT is kind of having 64 bits output. So again, what I do, I have 64 inputs, right? This is my OFDM symbol, and then I do FFT of it. So my IFFT of 64 inputs is going to be 64 things I'm sending out. It's going to be this funny phased waveform, which you can't really interpret in time because it's just sum of these signs. And then it's going to be 0 afterwards. Now, when I now add, this is without channel, right? So now if I add channel, this is basically what I did. Again, this is the same code, right? I just added this channel. So the channel is simulating this multi-path thing we were doing before, right? And so now we see that before it used to stop here, and now it's going even further, right? And so this is just the effect, and I think I have this on slides, right? So this is just the effect. This was the first case, right? And this is the second case. So essentially, I mean, kind of obvious, we had this pulse which was kind of repeating in time. Now this whole thing is being repeated in time. But keep in mind, so we have this one, and then we have a delayed copy of this one, shifted by one, superposed with that one. So not only this end is kind of interfered with, everything is interfered with, right? So you see that doesn't really look the same. This is completely kind of different, right? So the worry is, okay, how do we deal with this right now, right? So we kind of screwed up everything. Okay, are we able now to recover this waveform now, because it doesn't look at all the same, okay? But that's the beauty of OFDM, that we are able to do this very simply, and we'll see on the next slides, because of this thing that we're doing in frequency. And so I guess, so let me just give you a brief idea. Again, I said I'm not going through all the details of the derivation of this, but the idea why we can deal with this multipath in frequency is that if I have a sine, right? So think of a sine lasting forever, right? Take this sine, I shift it in time by something, and I shift it in phase, right? I sum it up with the other sine. They both have the same frequency. The sum will have the same frequency, right? So what happens is I'm changing the amplitude and the frequency of this, and sorry, not the frequency, amplitude and the phase of this sine, but I'm not changing the frequency of a sine, right? So that's the key observation for OFDM. So that's why we do IFFT, to encode our symbols in sine. So when we look at the symbols after the FFT at the receiver, all this mess up happened, but I know the effect of this mess up is going to come only from my own sine, right? Because of the math of this saying that these signs are eigenfunctions in this space, whatever. So basically, if you do this linear transformation, and this channel impulse response is a linear transformation, just doing delayed shift and sum, right? Then what happens is I'm going to interfere only with myself on the same sign. All other signs will stay completely orthogonal to it. And there is a very nice math behind it, but again, I'm not going to do that. That's the intuition why we want to do IFFT before. So make sure every symbol is encoded in a sign, and when different signs interferes, I mean, when the multipart happens, my symbol interferes only with itself, right? Not with other symbols. So if you look in time, obviously that's not the case. That's why CDMA has to do all the equalization, to look at the, it has to have low cross-correlation and self-correlation and all this stuff. Here, it comes for free, right? But there are certain things we need to do, and that's what I want to show you, like why do we add cyclic prefix and all these things. So basically, again, in time it looks completely different. So now, what are the effects of FDM symbol in frequency? Let's look what are we going to do next. So now, what happens in frequency? So what I'm going to do now, I'm going to now look at a bit of a receiver, right? So this is, again, a very simple receiver where I don't worry about any time synchronization, frequency, everything is great. So it's the same as before. I'm taking some random bits. I'm modulating let me run it while we discuss. Turns out to work fine. So I'm sending some random bits, right? I'm modulating the random bits, getting QPSK. Then I'm doing IFFT, okay? Now I don't have any channel, so I do just FFT. And then I plot that. So basically what I should get is this one cancels this one. I just get modulated QPSK, okay? So let's see. Yeah, that's it, right? So these are the symbols I'm sending. They're QPSK symbols, and here I'm just plotting the real part. So maybe there'll be some change in the complex part, but this is enough for the thing. So essentially, if there is no channel, my receiver, which consists of IFFT and FFT, will cancel each other, and I get my symbols back, which is what I want. So the question is, why do we do all that? Why don't we just send symbols, right? So now what happens if I add channel? So once again, right? So this thing here, what I'm doing, I'm not doing anything special. I'm just saying, okay, I'm reading bits, the same thing here, modulating, IFFT, and I add the channel again, right? Seems I'm missing the FFT here. This was the same time thing I had up there. Maybe I just deleted it. Okay, we can add this easily. Okay, so you can believe me, it's easy to modify the code here. Again, I'll invite you to do this in Sora in 5 seconds. Okay, so it should be right. So basically everything is messed up. So I'm doing right now, right? I'm doing the thing. So basically what I do, I put a channel in between, right? So the fact that I did, that I put this thing inside. So my modulated symbols, even though I kind of did the FFT, right? They didn't do what I just explained it should do, right? And so what is the reason? The reason is the following. What happens is, because if you look at each of these signs that we saw initially, right? So the sign gets summed with various copies of itself, right? So even though I don't interfere with other symbols, I interfere with myself, right? So my phase gets moved and so on. It gets moved in a very predictable way, but it gets moved. So we can't just do this, right? Do test channel and test IFFT. What we need to do is channel estimation. So what channel estimation does, it says, what kind of summing of these things will happen, right? So I'm going to have a delayed sign with different phase and so on. So there'll be a transform of this my phase and so on of the initial symbol. So what I have to do, I have to figure out what it is and then remove it from the rest of my data points, right? So that part equals equalization, and that's essentially removing the effects of multipath channel, right? So that's the next demo. So basically what I do now is, let me run it again while we discuss. So now it's the same kind of code, except that I do this invert channel, right? So, okay, so what this invert channel is doing, this is the channel estimation. So now what I'm saying is like, let's see, knowing what I send. So that's why we send this pilot for probing, okay? So what I say now is, channel is doing something for my symbols, right? So it's quite easy. I'll send a known symbol, right? The channel will do something to my complex symbols. I remove the channel by dividing by this complex number. So I send a complex number, which is QPSK maybe 1 plus I1, or whatever, -1 minus I1. I send this. It gets multiplied by some unknown channel effect. And when I receive it, I divide by what I send because I know it's my pilot, and I get the channel thing, right? So, so this is what I do. And okay, so now this is all 257. Okay, the scale is weird. So why is it all 257 with a little bit of thing here? So it's basically because it's just a precision issue. It's constant. So why is it constant? I didn't put any channel, right? It was just a straight thing. So I inverted the non-existing channel, so there is no transformation on my thing. So if I now add the channel, right? So now again, okay, let's run it. So now again, I have this IFFT, the same thing as before. I just add test channel. So what I do, I say test the IFFT, test channel, FFT, and then invert channel. So this is just taking the next symbol and inverting with a known one. So I get something funny, right? And these are now large numbers, 500, right? It goes -1 plus 100. So this is over 64 subcarriers. So each subcarrier has a different effect. And this should be complex numbers. I'm just plotting the real ones, right? So each subcarrier, the phase that I was sending, this nice QPSK symbol initially, gets multiplied by this unknown effect of a channel. And then we get these weird things, right? And unless we know what this thing is, we can't really recover it, right? So let me just quickly show you what this channel preamble. Let me just quickly show you what this channel estimation does, just invert channel. This is the code we use to invert channel. Just to give you an idea, I mean, the promise is to explain you how to build a full Wi-Fi receiver, so you should understand most of the things, and it's actually in Sora. So what this thing is doing, it's really dividing. It's really dividing the known. So I send a symbol, one QPSK symbol in each subcarrier. So I send 64 QPSK symbols. I receive them. They have this weird transformation. I know what I send because it's my known preamble, and I divide what I received with what I sent, right? And so that's going to be my output of this. Now the trick here is that if you do this in MATLAB, you can do it like that, right? You can do a complex division of floating points, but that's really slow. So you need to do an inversion in fixed point, right? And that's something, that this language, or I mean, you have to do other tricks to actually map there. And that's a different, difficult problem, but it's a little bit of designing issue to do this kind of inversion in floating point. So you don't really want to do a full division, and you want to make sure when you divide, you're not doing, you don't lose the precision. There's a little bit of code. Actually, all the operations are quite simple. So conjugate multiply. So you take this guy, you multiply with itself, conjugate, and to get the the norm of this guy. So it's just a multiplication with the conjugate you get, and this thing is 32 bits. So there's a little bit of issue with precision. That's something we cannot take away, right? Any kind of fixed point implementation, you have to worry about that. That's this compiler will not take it away, and So then the next, but this is orthogonal. There are languages that could deal with this. So we can hope to integrate something else which will go through all these calculations and we'll figure out what are the actual precisions and remove the precision issue. However, if you want to do a division and complex things, it's quite difficult to do it to do arbitrary expression to move from floating point to fixed point. I mean, it's quite difficult to automatize this. So this is something you as potential designers will have to think about, right? So that's just the key point. But essentially, it's not too much. Basically, you go and you calculate again the conjugate multiplication. You have to normalize with the thing, so you don't lose your precision. So it's a little bit of manipulation over the vector, right? And the only thing you need to worry about is basically for each one, if the norm is too high, how you normalize and so on. So this is all about this normalization code. For each of the subcarriers, right, you need to do that. And here we do that we're using vector instructions, so because it's running automatically as SIMD, so it's really fast. Right, so I'm going back to this guy. Okay, so now we plotted the channel, and now we want to equalize the channel, right? So now I say, okay, okay, so now I said, okay, I did my channel equalization. So now I'm able to learn what channel does to my signal. So the idea is the following. I take the preamble, okay, as we said. I look at what preamble does to my signal. I learn the channel vector, and then if I divide every subsequent OFDM symbol by this channel vector, I get my symbols intact, right? So as simple as that. So that's what Wi-Fi is doing, that's what every single receiver is doing there. You do some channel estimation in OFDM, right? And that's called equalization, right? And equalization you have to do basically removing the channel effects. You have to do in every physical layer, and it really depends what is the complexity of this thing. So here, it's nice because it's just a set of complex multiplications, right? In other receivers, it could be much more difficult. So let's see what this guy is doing now, right? So we just say, okay, so we're doing the same thing. This is our mock, this is our mock transmitter. We send, we modulate, we do IFFT. Okay, this is there is no channel here again. I just want to test it. Test FFT. I get the channel inverter. I get the channel, right? So what it means, I have to send multiple symbols. The first one is my preamble. So this guy is going to be executed in sequence with that guy. So first I'm taking the first 64 symbols and doing channel inversion. And then with the rest of it, I use this channel to equalize and get the nice symbols out. Okay? So it's kind of simple. Now, first you do that on the first symbol, and then afterwards you keep on, for all the symbols doing the next bit, just equalize, equalize, equalize. Right? And I get nice symbol back again. But why do I get nice symbol? Because I don't have any channel. I was cheating, right? I just wanted to say that since my channel was flat, okay, I did my inversion. So at least I didn't do any stupid mistake in how I take my bits. But there's nothing special here. There's no channel in between. This is the code that look like. Okay. So now I'm saying, okay, let's then put a channel in like we did before. Okay, so now it's really the same. I still do this is the part that's the transmitter. I do the modulate IFFT, then I put the test channel, and I do the inversion. Okay, so we are hoping it's all working fine now. But not really. Still get a big mess, right? Okay, so why do we get a big mess? So, okay, this was the thing we saw before. If I just do the, if I don't equalize, I'll get a big mess as well. Now this was the estimated channel. But now the problem is that if I have a channel and I do this equalization, I still get a big mess. So why do I get a big mess? So here is what really happens. I'm sending one symbol, okay? And I'm sending the next symbol. Now, this symbol is doing this delayed multipart, right? So this is my multipart effect that, as we saw before, right? It spreads out, right? If you remember the figure, right, so this is the original symbol, but it spreads out. This is the bit that hangs out because of the multipart, because of the delay. So that's the bit in blue there, right? So that's there, right? So it actually interferes with my own symbol, right? So I'm still getting these bits out, and you know, they're messing up my nice. So in effect, I'm addressing my own multipart inside, but I'm having a problem from multipart from the previous symbol, okay? So what I want to do is I want to add cyclic prefix, right? So to add a little bit of gap between, so to make sure, sorry, I want to add the gap. I'm not yet cyclic prefix, I have to explain that yet. But I want to add the gap, which is kind of proportional to the size of multipart, right? So to make sure that this guy doesn't affect my receiver, okay? But then, keep in mind that I still have the interference from myself, right? But that is nicely taken care of by OFDM and FFT, right? Because I have these things there, right? So now I'm hoping if I do this, I'm done, right? So now I'm going to do this, right? And I'm going to add cyclic prefix. Okay, so what I did here, I basically run this guy. So everything else is the same. I'm just running this guy. And I'm also changing the receiver because I need to be aware I have to skip this gap. So there's nothing much there. And I can show you the code for IFFT with 0 cyclic prefix. Right, there it is, right? So basically, I'm taking I'm taking some input. And my output is 80, right? So I'm leaving the gap at the beginning, as we wanted. And I just copy the data that I created the FFT into the okay, it's the first, but then you know the gap will be at the end of the previous symbol, right? So I'm inserting gap. Essentially, I'm leaving the last bits empty. so I don't overlap with multipart. Okay, so we're hoping it's going to work, but it's not. Okay, and okay, I guess many of you that might know why it's not working yet. Anyone? What am I still missing?
You need to put the end of the second block onto that.
Right. So that's what is called cyclic prefix. It's not enough to put 0. You actually need to put a copy of the block on the other side. So, so basically, what I need to do is I need to take this part and put it there. So it sounds quite random, but essentially what I'm doing is I'm making the signal periodic, right? So my own signal is periodic. The problem is, right, if you think of the multipart, so this guy's multipart is getting, is kind of fading out, right? The problem is my signal starts here, right? My signal starts here and it starts abruptly, right? If I put my FFT around here, I'm not seeing this abrupt start. I'm seeing exactly the thing I want to see, except there is multipart, which delays the abrupt start of this guy, and I actually see it as a delayed copy in my own signal, right? So that's screwing me up, right? So I can't really, I mean, that's what messes up the whole thing, and I still don't get my nicely equalized thing, right? I still get a bigger mess because I haven't really taken care of self-interference for myself at the beginning, okay? So what I do, I take this bit here and I put it there. Now if you remember what we created, they're all sine forms, right? So basically, so FFT is a big sum of sines, right? I had these two sines, I summed them up, I had more sines, more sines. So really, if I copy that here, it is equivalent as having these sines just extended, right? So if I take this copy here, you wouldn't even notice, right? It's just a sine. If I take this copy here, you wouldn't even notice, it's just a sine, right? But if I do an FFT here, right, then, you know, I'm seeing, this thing won't affect me. But what is nice here is that the multipart, if I take this guy here, then all the multiparts I'm seeing are still a sine, right? So they all adhere to the same FFT rules that they're orthogonal to themselves. Now, if I don't have a sine here, this function is not really a sine. It's a kind of heaviside function with the step function with a sine, right? So if I do an FFT of it, it's not anymore adhering to the rules that I had said on nice eigenfunction and all that. So essentially, what we need to kind of what we need to add here is really the cyclic prefix and non-zero cyclic prefix. I mean, not just a gap, but with cyclic prefix, right? So while I'm doing it, so okay, so what's the difference here? The main difference from before is just I don't have this zero CP, but I have CP, right? And here I don't care. Here I basically just, at the receiver, I remove the cyclic prefix completely. I don't care about the symbols that were cyclic prefix. I care about their delayed copies that come and bother me, right? So I drop them out. I do the same thing. So again, if you look at the transmitter, so the transmitter part is the IFFT with cyclic prefix. So IFFT with cyclic prefix, this is the one here. So it's really the same. I'm just doing the, no, this is FFT. Sorry, I need IFFT. So this is IFFT with cyclic prefix. Let's do it like this. So basically, I do the same thing here, right? So this was the one without cyclic prefix. I was writing into the first 64 parts, and I left because the output vector is 80. The other 80 were just zeroed out here, right? So I create an empty vector of 80, and I do the FFT only writing in first, and I left the rest empty. Now here, I'm actually writing the FFT, okay, in the last part. It's just, I should have done it the same way anyway, but it won't make a difference. So I'm writing the FFT in the last part, my useful FFT. I'm just taking the last 16 bits and copying in the, sorry, they're not bits, they're complex numbers. I'm taking the last 16 complex number and copying them in the first 16 complex number. That's it, right? And then I'm sending that. So now, where is my nice signal? Let's see what happened. Probably have a new form now as well. Not this one. Okay, I think this is it. So Right. So that's my signal back, right? Nice as I sent it. So the issue, okay, you see that it's a little bit ragged here because we did the inversion of the channel. There's some precision issues, but it's pretty clean, right? It's a little bit, probably like around 1% of error. So you can have a very good clearness. Now, of course, the precision of inverting it depends on the way the precision of your receiver, AD conversion, and so on. But this is quite a good one, 16-bit, right? It's more than you'll ever see in most of the commercial things, right? So it's really simple, right? If you look at it, this is our entire Wi-Fi receiver, right? Okay, there are synchronization issues. I'll talk about it in a moment. But basically, we're having like, okay, modulate, do the channel inside, and the receiver, what you do, you first do FFT, right, with cyclic prefix. So you need to put a cyclic prefix in the transmitter. At the receiver, you need to just get rid of cyclic prefix. You just need it to make sure that what you get from the multipart inside is removed. And then you do inversion to get the channel vector. So the first symbol, or wherever you start, has to be your channel estimation. And then you equalize every next symbol, you equalize, and you pass it on. And that's it. You now pass it in the decoder, demodulator, and all that. You're done pretty much. That's OFDM, right? So Wi-Fi, LT, WiMAX, it's all that, right? And you know, it's no more. Okay, there's some code in there, but it's not much. I mean, I showed you every piece of the code, right? The only complexity, I mean, vector multiplication is a library, right? It's like an SIMD. It's not a rocket science. The only thing hidden was FFT, right? And FFT is really the SORA efficient implementation. That's, you know, it's really standard FFTs, you know. So that's about it, really. And so there is one more thing in. So I have to go back. There is one more thing to mention. Here is that. So this was. So you have to do this, right? And so this was thing with missing and with the correct cyclic prefix. Okay, so Scrambler. So the interesting thing about Scrambler. So why do we use Scramblers? We use Scramblers to get to avoid large peak to average power ratios. So essentially, here is the problem. Let me. Okay, so here. Here what I'm doing, I'm taking input, modulating the same thing as before, and I'm doing IFFT, right? So, but this input now is different. You don't see it. It's just the sequence of zeros, right? Just sequence of 0 bits, right? So now, I'll have to get this guy out to see anything. So you can see already, it's just the, let's see, 80. So just one peak here, right? One peak and all zeros, right? So why is that? So basically, I'm sending all zeros everywhere. And so when it all sums up, right, I have this is the FFT of it. It's just a pulse, right? So if you think of it, right, if you do, what is the spectrum of a pulse? Has an infinite spectrum, right? Not infinite, but whatever your bandwidth is. So if you send the same symbol, so when I say send all same symbol, it's actually, let's say, one complex number, 1, 1. So I have a full spectrum, right, of same symbols. When I sum it up, I get a peak, right? So this peak is definitely not good. And why is this peak not good? That's one of the problems with the OFDM because of peak to average power ratio. So you have to normalize you have to put your digital to analog converter after this. And your DAC is going to saturate here. And if it saturates nonlinearly, it's going to clip it and going to destroy things out there. So basically what you do, you basically have to just add a Scrambler. So a Scrambler is this pseudo-random sequence that we were looking at for most of the talk, right? And so I just basically added it here. So it's just going to randomize the thing, right? And when it randomizes the thing, then you're going to get something which is much nicer. So the peak was 6K, right? Now everything is kind of biased and in the same range. So your ADC, so DAC is going to behave much better. Now, of course, you can say, well, you know, I can send something that when I scramble it, becomes all zeros, right? So scrambling is just one-to-one transformation. If I go from a set of codes or possible words, I can end up in zeros as well. But it turns out that if you look at lots of things you're sending, like header will have lots of zeros, you know, packets you're sending will have lots of zeros. So having all zeros is much more likely to show up than having some random things. So the scrambling helps really a lot, right? And So that's the explanation from Scrambler, right? So these are the things there. And so this is the full receiver. So we need this remove DC for the detection, and I'll kind of briefly describe that next. And then we have parameter estimation. This is what we've seen, right? We do channel estimation, and then remove cyclic prefix. We do FFT. We do channel equalization, and then we do pilot track, remove pilots, and receive bits. So the receive bits really is the digital part. So you do bit-to-bit decoding, and that's kind of, I'm not touching it. It's kind of standard. So, and I don't have time much to talk about it, but you should kind of understand, except for this guy I'm going to talk about in a bit. You should understand most of this, and this guy I'm going to mention this now, right? So this is really the receiver, and it should kind of all be familiar to you. This is enough to run the proper Wi-Fi transmission in the air over, tens of meters, I guess. Depends on your radio and all this stuff, but there's nothing much to it. So, if you understand this code, you can take it and play with it and do research on it. It's really simple, I think. Okay, so now just pilots and detection. So pilots are that's difficult to demo because pilots are used. In an ideal system, you don't need pilots. You would just use this channel estimation and go on. The reason pilots are used is if you do channel estimation at the beginning of your Wi-Fi packet, and then as you keep going, right, your channel might change. So because your channel might change, right, it will change a little bit, not too much, right? And the other issue, you will have a frequency offset potentially, or my clock is different than yours, and all these kind of strange things will happen. But there are small epsilon changes, right? So the way you monitor these epsilon changes, you look at the pilots. And pilots are really like a small preambles which you know of. So you do the same kind of algorithm. It's really the same thing in version over the pilots. But then you interpolate over all the data points. So it's kind of a small additive improvement, but it's quite important. It's fundamental to actually make it work. But there's no extra logic. It's really the same thing. You just have to think of it having, you did this basic estimation initially of the whole thing, and now you keep track, just devoting a little bit of parts in frequency just to keep on estimating. It's the same idea, the same code. So I'll put all this code online. So if you want to, and there is the whole Wi-Fi transmitter and receiver already in a repository. So you can kind of go back to these examples, run them yourselves and all that. So, right? So, so carrier sensing and synchronization. So basically, the point of carrier sensing is to find where the packet starts, right? So all this was fine because I was sending from transmitter directly in the receiver, but usually you'll be out in the open, you have a signal coming, and you want to know where does it start, right? So how do you find where it starts? That's something you heard in the previous talk as well. There's energy detection and all that. But so carrier sensing is used for that, and also is used for this detection is also used for carrier sensing. So as we saw, the carrier sensing can be done with energy detection and can also be done with preamble detection. And it's actually down to the designers of Wi-Fi. Different cards can do it differently, and they do a mix of the two, right? And also it's used to estimate carrier frequency offset. And I'll skip that for now. But basically, you need the accurate timing, because if you shift your timing, then all the things we're talking about, you'll catch the multipart. You need to start these things at the right times. So this is a kind of an important block. Okay, so let me see. I'll skip I'll run the demo of the second one because I'm getting short of time. So this is yet another preamble. If you remember transmitter, we were sending two preambles. The second preamble was the one that we used for estimating channel that you saw. This is the first preamble, which really tells us where the channel starts. So this is this preamble in frequency, as you can see, and this is the actual Wi-Fi preamble. I just copied it. And these are the real numbers. So again, the preamble will be complex. They're the Q, which I don't show. This is the I one. So the interesting thing is that there are lots of zeros, right? There are a few ones. So basically these are the non-zero symbols. And in between there's zeros. Okay? So what does it mean? So if you work out the math, you'll figure out that if you put these gaps in between, this will define the periodicity of your signal in time. So if you look at a signal, it's not really very visible, but you can see that this guy is periodic with this guy. It goes down, look at this, and this guy goes the same, and this guy goes the same, and this guy goes the same. So there are 4 blocks which are repeating, right? They're exactly the same. And I was going to do the demo, but it turns out I'm short on time. But basically, if you run this, you will see that this is the outcome signal, and the gap between this is exactly 4. So 1, 2, 3, 4. So the periodicity, so the gap between the time, the signal and frequency will give you the periodicity in time. Which, okay, so why do we need this periodicity? So we need this periodicity to simplify detection. Okay, so I'll show you how you do detection, but just keep in mind that really this thing is periodic. Okay, so how do we detect preamble? So the easiest way is to do correlation, and that's something you heard about in the morning. But basically what happens is you start moving around, so your signal is coming, you're matching this preamble, matching, you're doing this match filtering or correlation, whatever you want to call it, and at some point here you have a hit, right? So you did this correlation, say this is my starting packet. Conceptually very easy. The problem is that this correlation is very demanding, right? So if you think about it, so this guy here, let's say this is a preamble of 64 complex number. So I'm doing the first one, and I have to correlate 64 complex number. This times this, plus this time this, plus this time this conjugate, and so on, right? So I do 64 multiplication at this point, right? But then, as I move, the next symbol, I do 64 multiplication. And that's at 20 megahertz, 20 megasamples a second. So it's a lot of calculations, right? And it's very difficult to do that. So if you don't, and that's the most demanding part of the actual circuit, right? So I have to do it across, right? So now the observation is, because there is periodicity, right? We don't need to do it as often, right? Because we have this, so if you think of it, right? So if I'm correlating here, once I move and correlate here, I know that these guys are the same. I only have to recorrelate this next guy, right? So I'm going to put this in my algorithm. I'm not going to rerun these because I ran it already, right? So, and I'm doing a trade-off in accuracy, and I'm going to show it to you now. So this is, I think, the last demo. Okay, so so what I'm doing here, I'm basically just sending the preamble in time, okay? So what you will see is now this is the preamble I'm sending. This is a kind of messy, no, it should, no, I haven't put it yet in. I have to close those guys. So I'm doing CCI, right? So I'm basically doing, let's see, what's the scale, right? So this is my preamble, and this is some random signal I'm sending, right? And I want to see how will that correlate, right? So what I'm going to do, I'm going to run my correlator, and I'm actually correlating 16 of this. This is the repetition part, 16 of this. Then I move for the next 16, right? So I can use this thing. And so now I'm just going to run the correlation. So what am I doing here? It's the same code, except that here I add correlate, right? And so what I do here, basically this block here is just taking and sending random 64 symbols so that I have a little bit of noise. Otherwise my correlation is cheating, right? If I have zeros and I see it. So this is sending some data from the receiver. I put the preamble in it and I put the data out, which you saw before, right? And now I did a correlation. So here is my correlation, right? And so you see, that's the thing. So as I move towards my preamble, this thing increases, right? And as I go beyond, as I pass it, it goes down. So, I can clearly see a peak, right? So that's the kind of simple detection. And, you would do that with the same detection. Now, the reason, what do we lose by doing this repetition, right? You can see that this peak is not very sharp, right? And the reason it's not very sharp is precisely this repetitions. Because the guy who is next to me, right? He's going to be very similar in the level of the peak. And so how do I detect peak? I basically say, well, okay, the simplest algorithm would be I store the 3 previous ones. So I'm looking for the pattern which goes up and down, right? So here I don't see up and down. It go up, they all go down. This guy goes up and down. But if I have some channel problems, here's channel issues, some interference, so on. My bump might occur here or here. So I lose some precision in my timing, right? I can do this earlier or later. But as a trade-off, I actually get the easier, the better correlator. And so I'm just going to actually show you how this correlator works. It's not super difficult, but it's actually instructive for that. So one thing I do basically is this correlator pattern, right? So again, this is Sora design. So the credits goes for them for the design. We just kind of implemented here in a simpler way. So what you have to do is, first thing, how do you correlate, right? You can do these shifts and correlate as we had in the example here, move around. Now the problem is if you do it in vectorized code, in Intel SSE instructions, your vector has to start to be 16-bit aligned. So you cannot arbitrarily move the vector. So you can actually move only by 4 complex numbers. So the trick they do, and it's a quite neat trick, they basically create all the rotations of the preamble, right? So when they take these 4 bits, because the preamble is already cyclic, they just correlate with all the correlations. And these are our patterns, which are just the original preamble just shifted by 1. You just shift by 1, by 1, by 1. So you have all the circular shifts of the preamble pre-computed, right? So when we go and actually do the correlation, so for each of these, right, we do 16 correlations, right? We do 16 correlations with different circular shifts, right? So any of these circular shifts could be a hit. But then we don't move by 1, but we move by 16, right? So it's really the same, but the only difference is because of the nature of the computer architecture underneath, we can't move by 1 because our SSC buffer is defined by 4. So it's a trick, and this is something a compiler, as far as I know, wouldn't be able to do, at least not ours. So it's quite difficult optimization. So there's still some human thinking involved, right? But these kind of things are, you can make this as a kind of a function, which is kind of a standard, so you can kind of use it. But the point is that there is some thinking you cannot completely forget about underlying architecture, but it's still kind of quite and actually this is the entire correlation code. It's 1 page, right? So the other trick, and this actually comes from the Wi-Fi design, because of these repeating preambles, you don't really need to correlate again, but you just store the previous correlation. So you have this window of correlation history that just shifts, right? And you're reusing this information from the window, and you're kind of just running it there. So as a final demo, okay, so you might ask, what about performance? So I'll try to, let me just understand if I put everything in there. No. Okay, so I should be running the same thing in a test mode. So okay, so now what I'm doing here, and I'm hoping it's gonna finish nicely, so I can hope it's not gonna be an embarrassing number. Sorry, I forgot one more thing. So what I'm doing here is basically I'm compiling the same code, where I just have the correlator, and I'm running with all these options with vectorize everything to have a very high throughput output, right? And so it's kind of doing something all behind your back. So you saw the code, that was the code, the same code. So the only thing I just would correlator read and write, okay? So then what happens, and it's kind of simple profiling by the compiler, which shows you what you can do with kind of with the flexibility you have. Now I run this, okay? So this is the command line that I ran. I just say input is dummy. I send zeros, okay? And the output is dummy. I don't have any input and output. I just send the same buffer, 0 buffer again and again. And I do it 100 million times, right? So I'd send a lot of it. And it allows me to profile entire my block, right? So the key question I have here is basically when I do this, right? What is the throughput I get? I need to be able to do this at 20 mega samples a second. Otherwise, my Sora design is not working, right? It's too slow, right? And because I'm designing it from CPUs, right, I don't have any guarantees this works fast enough, right? I need to test it myself. If you design the FPGA, you know the clock, right? You might have too much space, but it's going to work fine. Here, with CPUs, the key trick is actually you need to make sure it works fast enough. So this is a great way to measure it, right? You just run this, and here's what it takes. It takes 2.4 seconds, right, to run 100 million samples. So it's roughly about 40 mega samples a second, right? And we need 20. So we are good, right? So I can say, and it's double the limit. So I can say safely that I can run this in any design. And if you think about it, this is the CCA block, which doesn't link into anything else, right? Once you detect, then you go into everything else, right? So you can test CCA block in isolation. And the nice thing is that that's the kind of the separation of data and control flow. You don't really care whether you have all zeros or you have whatever you have as a data, because it's just a detector. It's just doing correlation. So there is no control path inside. And you actually do accurate measurement of performance with this. You don't have to worry about whether you touch all parts of the code and so on. So essentially we know now safely that this can be put in any other architecture as long as it's standalone. And we can do the same, and that's what we do with this profiling. We profile different parts of a chain which have different control paths to make sure they're all fast enough, right? And this is a kind of as good as it gets in Sora to tell that actually your design is good enough and you won't that you know you're not breaching the timing. So basically, the bottom line is this code here is relatively simple, supposedly quite easy to read, right? And okay, there's a little bit about this move, but it's really not much. The algorithm is all there, right? And it runs fast enough to run the real-time thing, right? So that's the kind of bottom line. And so we basically went through the entire, going back to it, we basically went through through this entire guy, right? We now understand this, we understand pilots. This bit is kind of a standard thing. So this is it, right? This is the whole Wi-Fi receiver. And the transmitter is really the signal processing part. It's just IFFT with adding cyclic prefix. So, you know, I think if you understood these bits in about an hour, right, I think you are safe to go and play with it yourself, right? And that's my hope, that after this, you know, you'll be really excited to try it, right? Okay, so that's the last bit. So conclusions. So basically, wireless innovations happen and will still happen in this intersection between fine and Mach layers. You have white spaces or other types of spectrum you might use. You want to do sensing there. You need blocks to do that. You want to go to 60 gigahertz. You have different issues there. So you want to do these interactions. There are new standards coming, new challenges, and so that's why you can do it in software radios where you can do these innovations. And we need prototypes and test beds to better evaluate these ideas. You can do simulation, you can do only so much. You really want to do the interaction with the rest of the system, the real wireless channel, the real challenges, and so on. And so physical layer programming, I think, is still in its infancy in terms of programming tools. And I mean, whoever used it, I haven't found anyone who's really satisfied with it. There's lots of things. So this is our, so basically difficulties, it's difficult to use, to learn. There's lots of optimization you have to do. And there's limited portability and scalability in a sense that, you know, you have to, it's difficult to learn. And everyone I talked to took some time to learn it. Difficult to compare with other people. If you run another platform, you can't run your code and extend previous work. So basically, the bottom line with this is that we have our, so this was our goal to make, our take on trying to make the wireless physical layer programming easy. And hopefully I persuaded you it's easy and it's fun, so you can go ahead and play. And lots of these free things are here, so you can just download them, get them, and play with it. So that's about it. So thank you. And any questions? If I still have some time. Yeah.
You showed the example of running it 100,000 times or 100 million times, and said that and then we are able to meet the requirement. But in that example, we gave the same input all the time. Would it have mattered if the inputs are different? Because this is running in CPU. And then if you have different data, loading data and doing some lookups, which means there could be some kind of loads kind of stuff. So what is your thought on performance from that part?
Right. So I think, yeah, it's a good point. I think, so one thing we're trying to do with the vectorization is to schedule in larger chunks. So one block runs over multiple larger chunks. So that will avoid lots of locality issues, right? The other issue is also if the code is more complex, you have different ifs and so on. So actually the correlator is mine. I mean, I wrote it from scratch. It's not the Sora code. And theirs is more difficult because lots of ifs, lots of states. But this one is simpler and it also works fast enough. So we kept this one. Because the code is simple, you can rely on that. So there are these ifs. But so here, because that's the best thing you can say, the whole argument here is like we're double the rate requirement. So hopefully, I mean, I haven't seen that then. So of course, the next test that this test we're doing is actually sending the real signals. And if you receive 100% of your packet, you're good, right?
How about simulating a network? Like you have multiple transmitters and receivers, and can you simulate it in kind of almost real time? This thing.
So we haven't tried this. It's a good point. I mean, it will still be fast, right? So yeah, maybe. So you have to integrate it in. We had another take on previously on a simulator where we kind of virtualized the physical layer, but we never did more really integrated this. So if there's interest, I think it's a good idea. Yes, maybe can speed it up. I don't know how fast it'll be, but.
But I think the point is that you could actually, instead of a simulation, run this on multiple computers and actually see for real, right?
Yeah, that's
better than a simulation.
Yeah.
Yeah. Any more questions? We can take probably the last one. Okay, so I think we should thank Bozhidar. So you guys must have written all this stuff in MATLAB, right? You must have sort of done this channel, whatever he showed, right? Send sine waves, run a channel, some channel on it, and all this kind of stuff. Now, he did similar stuff, but the difference is that you can actually make it go on the air, and you can actually see what is happening for yourself in reality. So this is as easy as MATLAB, if not easier.
That's the message,
right?
exactly.
But you can also make it run.
And you'll
in
be
real
able to
time.
get this code and do it yourself. You need to have Sora boards, but then you can just
Yeah.
run it on there and you can do real time. Yeah.
Right. Okay. So let's thank the speaker now. And we have this token of appreciation for you. It's a tribal painting, and thanks.
Thank you. Thank you.